Picture the very first moment of everything a silent, pristine emptiness, a blank slate of perfect order. It's a stillness so profound that it feels almost sacred, an origin point before stars, before light, before structure. Yet within that quiet, something stirs, not a voice, not a law, but something far more mysterious, entropy. Often misunderstood as mere chaos or decay, entropy might actually be the universe's first and most fundamental language, the hidden script that wrote existence itself into being. What if the birth of the cosmos wasn't about divine command or mathematical certainty, but about the elegant, inevitable unfurling of disorder? This isn't just a poetic thought experiment. It's a scientific frontier that challenges how we see reality. From the smooth, uniform soup of particles just after the Big Bang to the intricate galaxies and conscious beings we are today, entropy hasn't been tearing things down, it's been building them up. It's the force that gives time its arrow, that fuels the evolution of stars, and that even whispers in the workings of our own minds. We're going to explore how this seemingly simple concept, this measure of uncertainty and possibility, holds the key to the universe's greatest story, the story of its own creation. So prepare to see the cosmos in a completely new light. We'll travel from the origins of space and time to the farthest edges of theoretical physics, meeting brilliant minds and groundbreaking ideas along the way. This is a journey into one of existence's deepest mysteries, and by the end, you may never look at disorder or order the same way again. Let's begin. Picture the cosmos in its earliest moments, a realm of overwhelming heat and density, where the very concepts of space and time as we know them begin to take form. This wasn't a chaotic explosion in the way we typically imagine, but rather an expansion from a state of almost unimaginable simplicity. Every particle, every ripple of energy existed in a smooth, uniform distribution, a cosmic canvas without brushstrokes, a silent ocean without waves. Scientists refer to this as the primordial singularity, a point where the universe held its lowest possible entropy. Think of entropy not as mess or disorder in the everyday sense, but as a measure of possibility, of potential for change. In this beginning, that potential was at its absolute minimum. The universe was, in a way, perfectly ordered, but it was an order so profound it was featureless. It held everything within it, yet had expressed nothing. Renowned physicist Roger Penrose describes this state as one of exquisite precision, a configuration so specific and unlikely that it seems to demand an explanation. Within that hot, dense soup of fundamental particles, the seeds of all future complexity were present but dormant. The gravitational clumps that would become galaxies, the nuclear forces that would forge stars, the molecular bonds that would eventually create life, all were contained in that initial conditions, waiting for the right signal to start unfolding. This is the central mystery of our origins. How does a universe that starts in such a state of bland uniformity transform into the spectacularly structured and diverse cosmos we observe today? The answer may lie in understanding entropy not as a force of destruction, but as the universe's primary creative instrument. That initial low entropy state was like a coiled spring, or a writer facing a blank page full of potential. It represented a tremendous amount of stored information, a narrative tension waiting to be released. The universe's first act wasn't to speak a word of law or command, but to allow this spring to uncoil, for the entropy to begin its inevitable increase. This shift, this gradual move away from perfect order, is what set the entire cosmic story in motion. It provided the direction, the arrow, that would allow time to flow and structures to form. Without that carefully set initial condition of low entropy, the particles would have remained forever mixed. Gravity would have had no irregularities to amplify, and the cosmos would have stayed a static, lukewarm fog. Instead, that pristine starting point became the first sentence in a grand epic, written in the language of increasing possibility and unfolding change. But to truly grasp how entropy could be the universe's first language, we need to move beyond the common misconception that it's simply a synonym for chaos or mess. In reality, entropy is a subtle and profound concept. It's a measure of possibility. Think of it not as disorder, but as uncertainty. It quantifies the number of different ways the components of a system can be rearranged while still looking the same from the outside. A deck of cards fresh from the box with all suits in perfect order has low entropy. There's essentially only one way for it to be arranged as a new deck. But once you shuffle it, the entropy skyrockets. There are trillions upon trillions of possible sequences, and almost all of them look to us like a random, disordered deck. The high entropy state isn't about being messy, it's about having a vast number of possibilities. In the world of thermodynamics, this idea translates to the dispersal of energy. A hot cup of coffee in a cool room has low entropy. The heat energy is concentrated in one place. As the coffee cools, that energy spreads out, dispersing into the air until everything is the same lukewarm temperature. This is the high entropy state, not because it's chaotic, but because the energy has now found its way into a vastly greater number of possible arrangements. It has reached a state of higher probability. This inevitable journey from concentrated to dispersed is the engine behind the famous Second Law of Thermodynamics. But the story gets even more fascinating when we step into the realm of information theory. In the late 1940s, a brilliant mathematician named Claude Shannon at Bell Labs was trying to solve a practical problem: how to send a perfect signal down an imperfect telephone line without losing the message. He realized that the core issue was uncertainty, or noise. To quantify this, he needed a measure for the information content of a message, how much surprise it carries. A message that is completely predictable, like a string of the same letter, carries very little information, but a complex, unpredictable message carries a lot. Remarkably, the mathematical formula Shannon derived for information was identical to the one physicists used for thermodynamic entropy. He even borrowed the term, calling it information entropy. This was a revolutionary connection. It meant that entropy wasn't just about physics and energy, it was about meaning and communication. The higher the entropy of a message, the more information it could potentially contain. A perfectly ordered message is predictable and tells us nothing new. A message with some randomness, some uncertainty, is what actually communicates something surprising and meaningful. This fusion of ideas is where our cosmic puzzle gets truly compelling. If the universe's initial state was one of incredibly low entropy, that smooth, uniform soup of particles, then from an information perspective, it was like a message with almost no surprise. It was a single, simple sentence, but contained within that sentence was the potential for an entire epic. As entropy increases, as the universe expands and energy disperses, that potential information begins to unpack itself. The tiny quantum fluctuations in the early cosmos, which we'll explore later, were like the first bits of surprising data in that initial message. They were the seeds from which all structure, every galaxy, star, and planet would eventually grow. So when we ask if entropy was the language the universe used to write its first sentence, we're suggesting that the cosmos began with a simple, low information state, a foundational axiom. Then, through the process of increasing entropy, It began to elaborate on that sentence, adding clauses, paragraphs, and chapters. The dispersal of energy and the increase in possible arrangements weren't a descent into meaningless chaos. They were the mechanism for creating the rich, complex, and informative story of our universe. Entropy, in this grand view, is the syntax of existence, the grammatical rule that allows potentiality to unfold into reality. Now, this brings us to one of the most profound and inescapable laws in all of physics, the second law of thermodynamics. It's a principle so fundamental that it feels less like a rule and more like a statement about the very nature of reality. Simply put, the second law declares that in any isolated system, the total entropy can only stay the same or increase over time. It never decreases. Think back to that cup of coffee cooling in the room. The heat will always flow from the hot coffee into the cooler air, never the other way around. The concentrated energy disperses and the entropy of the entire system rises. This isn't a suggestion, it's a cosmic imperative. But the staggering implication of this law is that it gives our universe its most mysterious property, the arrow of time. Why does time flow forward? Why do we remember the past but not the future? Why can we break an egg but never unbreak it? The second law provides the answer. The increase of entropy is the physical process that defines the direction of time. The past is the state of lower entropy. The future is the state of higher entropy. This irreversible flow is why history has a narrative, why causes lead to effects, and not the other way around. Without this ever-increasing entropy, the universe would be static and timeless, a frozen sculpture with no past, present, or future. There would be no story to tell. In this light, entropy is far more than just a measure of disorder. It is the engine of change, the force that compels the universe to evolve. That initial, pristine state of low entropy after the Big Bang wasn't a mistake. It was the wound-up spring, the single, concentrated beginning from which everything else could unfurl. It provided the necessary gradient, the imbalance that allowed the cosmos to become dynamic. The gentle pull of gravity could begin to amplify tiny quantum fluctuations into vast galactic webs. Nuclear fusion could ignite in the hearts of stars, forging heavier elements from simpler ones. Chemical reactions on a young planet could eventually lead to the breathtaking complexity of life. Every single step in this grand chain of events, from the formation of the first atoms to the emergence of conscious thought, is driven forward by the relentless, universal increase of entropy. So when we consider entropy as the universe's first language, the second law is its most fundamental grammatical rule. It is the syntax that ensures every sentence has a beginning, a middle, and an end. It dictates that the story can only move in one direction, building upon itself, creating ever more intricate and improbable structures as it goes. This isn't a story of decay towards a meaningless end, but a story of constant transformation and the beautiful, intricate complexity that can arise from the simplest of starting points. The universe is not falling apart, it is unfolding, and entropy is the pen writing every page. Now, let's shift our perspective from the vast cosmos to the world of human communication, where a parallel revelation about entropy was quietly unfolding. In the late 1940s, a brilliant engineer named Claude Shannon was working at Bell Laboratories, tasked with a seemingly mundane problem: how to send a perfect signal down a noisy telephone line. His solution, however, was anything but mundane. It would fundamentally reshape our understanding of information itself. Shannon realized that the core challenge wasn't just about the physical signal, but about the uncertainty or the surprise inherent in any message. To tackle this, he needed a mathematical way to measure information content. What he developed was a formula that looked exactly like the equation for thermodynamic entropy, but with a profound twist. He called it information entropy. In Shannon's framework, entropy wasn't about energy dispersal. It was about predictability, a message that is completely predictable, like a monotonous string of the same letter, carries very little information. Its entropy is low, but a complex, unpredictable message full of surprises and variations carries a high amount of information. Its entropy is high. This was a staggering insight. It meant that the very concept of entropy, this pillar of physics, was also the bedrock of meaning and communication. A high entropy message isn't just random noise, it's rich with potential meaning because it contains genuine surprise. This bridge between physics and information theory is where our cosmic story finds its voice. If we apply Shannon's logic to the universe, a breathtaking possibility emerges. That initial state of the cosmos, the hot, dense, ultra-smooth soup of particles, was a system of incredibly low thermodynamic entropy. But from an information perspective, it was also a message with almost no surprise. It was a single, simple, compressed datum. It held a tremendous amount of potential information, but it was all packed into a tiny, ordered point, like a cosmic zip file waiting for the command to extract. The universe's first sentence wasn't long or complex. It was a single, foundational word of perfect order. Then the expansion began. As the universe grew and its thermodynamic entropy increased, that tightly packed information began to unpack itself. The process of increasing disorder was paradoxically the process of creating information. Those tiny quantum fluctuations in the early universe, which we'll explore more later, were the first bits of surprising data to emerge from that smooth background. They were the random elements that broke the perfect symmetry, the first nouns and verbs in the cosmic story. As entropy continued to rise, gravity amplified these tiny informational seeds into the vast cosmic web of galaxies and clusters. Nuclear processes in stars used this unfolding narrative to forge heavier elements, writing new chapters of complexity. And on at least one planet, this ever-increasing flow of information and energy allowed for the most complex information processing system we know, life itself, with DNA acting as a biological library written in the language of entropy. So, entropy doesn't just describe a slide into chaos. It is the mechanism by which potential becomes actual. It is the universe's way of speaking itself into existence, starting with a simple, low-information whisper and gradually elaborating into the complex, rich, and informative epic we see today. The dispersal of energy and the increase in possible arrangements is how the cosmos writes its story, with every galaxy, every star, and every living creature serving as a word in its grand, unfolding narrative. This line of thinking leads us directly to one of the most peculiar and mind-bending ideas in all of physics, the Boltzmann brain paradox. It all started with the brilliant but troubled physicist Ludwig Boltzmann in the late 19th century. He was a fierce advocate for the atomic theory of matter and the fundamental reality of entropy. He understood that the second law was not an absolute rule, but a statistical one. It's not impossible for entropy to decrease in a system. It's just incredibly, astronomically improbable. Think of our deck of cards. A truly random shuffle could, by sheer chance, return the deck to its original, perfectly ordered state. The odds are vanishingly small, but they are not zero. Boltzmann took this statistical view and applied it to the entire cosmos. If the universe is eternal and mostly random, then even the most wildly improbable events must eventually happen, given enough time. Given an almost infinite amount of time, a random fluctuation in the quantum foam of a high entropy, featureless universe could spontaneously assemble a fully formed, conscious brain complete with false memories of a past that never existed, hallucinating an entire universe around it. This hypothetical entity is what we now call a Boltzmann brain. The terrifying implication is that it is statistically far more likely for a single, disembodied brain to fluctuate into existence than for an entire, ordered universe with billions of galaxies and a long, coherent history to form by chance. You and I, and everything we perceive, would be far more likely to be one of these fleeting, accidental brains than the product of a 13.8 billion-year evolutionary cosmos. This is, of course, a deeply unsettling conclusion, and most physicists today see it not as a reality but as a powerful reductio ad absurdum, a sign that our assumptions are flawed. The paradox acts like a giant flashing arrow pointing directly at the most special feature of our universe, its incredibly low entropy beginning. The fact that we are not Boltzmann brains, that we observe a vast, coherent, and structured universe with a shared history, is overwhelming evidence that our cosmos did not start in a state of random equilibrium. It started in a condition of exquisitely specific, finely tuned order. This initial state was so profoundly improbable that it demands an explanation. It wasn't a random accident, it was a setup. It was as if the initial conditions of the universe were carefully chosen or written to allow for a long, complex, and coherent narrative to unfold. In the context of our exploration, the Boltzmann brain paradox suggests that entropy's first sentence was not a random scribble. It was a deliberate and precise statement, a declaration of low entropy that served as the foundational axiom for everything that followed. This fine-tuning is what allowed the story to have a plot with characters, events, and a timeline that makes sense. Without that specific initial condition, the universe would be a senseless jumble of random, disconnected fluctuations. There would be no consistent laws of physics, no stable atoms, no planets, and certainly no observers capable of understanding the tale. The paradox forces us to see that the universe's capacity to tell a story, our story, is not a happy accident, but is written directly into its deepest foundational laws. The first sentence was a carefully crafted promise of potential, a seed of order from which the entire epic of complexity could grow. So how did the universe get so big and smooth in the first place, setting the stage for everything that followed? The leading scientific theory points to a breathtakingly brief but transformative event known as cosmic inflation. Picture this: within the first tiny fraction of a second after the Big Bang, the universe wasn't just expanding, it was undergoing a growth spurt of almost unimaginable ferocity. Space itself stretched out at an exponential rate, becoming vastly larger in the blink of an eye. This wasn't a gentle unfolding, it was a violent, hyper-fast stretching that took a speck of primordial space-time and inflated it to a size much larger than our entire observable universe today. This process of inflation acted like a cosmic iron, powerfully smoothing out the fabric of the cosmos. Any major wrinkles, lumps, or irregularities were stretched so thin that the universe was left incredibly flat and uniform on the largest scales. This is why the cosmic microwave background radiation, the afterglow of the Big Bang, appears so remarkably even across the sky. Inflation gave the universe its pristine, ordered canvas. But here's where the story of entropy takes a fascinating turn. At first glance, this act of smoothing and ordering seems like it would be a massive decrease in entropy. And on a local density level, that's exactly what happened. By stretching space so dramatically, inflation dramatically diluted the concentration of matter and energy, effectively lowering the entropy density. It was like taking a single drop of ink and diluting it in an entire ocean. The ink is still there, but it's now spread so thin that the water appears almost clear. So, in that sense, inflation created a state of incredibly low entropy density, a perfectly smooth and uniform distribution. This is the crucial, finely tuned starting condition that the second law of thermodynamics requires, the wound-up spring of low entropy that allows the entire cosmic story to unfold. However, and this is the critical point, while inflation was decreasing the density of entropy, it was simultaneously and overwhelmingly increasing the universe's total entropy. How? By creating an enormous amount of new space. Think of it like this: entropy isn't just about concentration, it's also about the number of possible states. Before inflation, the universe was tiny. There was only a very small volume, which meant there was a fundamental limit to how many different ways particles could be arranged, a limit on the total possible entropy. Inflation blasted the doors off that tiny room. By creating a colossal, vast arena of space-time, it provided an almost limitless new playground for particles, energy, and possibilities. It created a gigantic stage upon which the drama of increasing disorder could play out for billions of years. The total entropy of the universe skyrocketed not in spite of inflation, but because of it. The smoothing was a local effect, but the creation of vast new volume was a global entropy bonanza. This dual role makes inflation the ultimate amplifier for entropy's narrative. It was the mechanism that took the initial, mysterious low entropy seed and expanded it into a grand, spacious theater. It wrote the smooth, blank canvas. But a blank canvas alone isn't a painting. The true masterpiece began with the next step. That incredible stretching of space-time didn't just smooth things out, it also magnified the tiniest of quantum fluctuations. These microscopic, random jitters in the energy field, which are inherent to the quantum vacuum, were once so small they were insignificant. But inflation stretched these tiny quantum ripples across the entire cosmos, imprinting them as faint, large-scale variations in density. These imprints are the seeds of all future structure. They are the slight gravitational over-densities that would, over hundreds of millions of years, attract more matter, eventually collapsing into the first galaxies, stars, and planets. In this way, inflation used the quantum uncertainty of the vacuum to inscribe the initial blueprint for complexity. So, we can see cosmic inflation as entropy's most powerful pen. It first prepared the vast, smooth parchment of spacetime. Then, using the ink of quantum fluctuations, it carefully dotted that canvas with the potential for all future structure. It was the universe's way of writing a prologue so expansive that it had enough room for every galaxy, every star, every planet, and every life form that would ever come to be. The increase in total entropy wasn't a descent into meaningless chaos. It was the act of creating the necessary space for a long, complex, and beautiful story to be told. And it was within that smooth, post-inflationary canvas that the universe's true creative process began, driven by a seemingly magical quantum phenomenon. We often picture empty space as just that, empty, a true void, but quantum mechanics shatters that illusion. According to this fundamental theory, what we perceive as a vacuum is actually a seething, bubbling foam of energy. At the tiniest imaginable scales, pairs of virtual particles and their antiparticles are constantly flickering into existence, borrowing energy from the vacuum for an infinitesimally short moment before annihilating each other and vanishing back into the nothingness from which they came. This isn't just theoretical, it's a well-tested reality with observable effects, like the Casimir effect, where two metal plates placed extremely close together in a vacuum are gently pushed together by the pressure of these quantum fluctuations outside them. This eternal, subatomic bubbling represents the most fundamental form of uncertainty and randomness in nature. It is pure potentiality, and in the first instance after the Big Bang, during that period of hyper-fast inflation, these tiny quantum jitters were caught in the act and frozen into the fabric of spacetime itself. Imagine a perfectly smooth, expanding balloon. Now, imagine that the surface of that balloon is itself made of a microscopic, shimmering texture. As the balloon inflates at an unbelievable rate, that tiny, shimmering texture gets stretched to an enormous size. Those minute imperfections are no longer microscopic. They are now vast, continent-sized variations etched across the surface of the balloon. This is precisely what inflation did to the universe. It took those random quantum fluctuations in the energy field and stretched them across the cosmos, imprinting them as tiny, fractional differences in density. Some regions were ever so slightly denser than others. These imprinted density variations, these fossilized quantum ripples, became the most important seeds in cosmic history. They were the universe's first rough draft, the initial clustering of matter dictated by pure chance. In a cosmos governed by gravity, density is destiny. Those regions that were a fraction of a percent denser had slightly stronger gravitational pull. Over hundreds of millions of years, that extra gravity acted like a magnet, slowly pulling in more and more matter from the surrounding areas. The slightly denser patches grew denser still, eventually collapsing under their own weight to form the first protogalactic clouds, which then fragmented into stars and planets. The slightly less dense regions remained and expanded into the vast, empty cosmic voids we see today. Every single structure we observe in the sky, every galaxy, every cluster, every supercluster, is a direct descendant of one of those primordial quantum fluctuations. Our Milky Way galaxy, our Sun, our Earth, and every one of us originated from a specific, random density bump in the early universe. This is where entropy's role becomes beautifully clear. Remember, entropy is fundamentally a measure of uncertainty and the number of possible states. Those quantum fluctuations are the physical embodiment of that uncertainty. They are the universe rolling a quantum die. The specific pattern of denser and less dense regions was not predetermined by any law. It was a random outcome, a product of probability. In this way, entropy provided the language of chance that the universe used to write the blueprint for all structure. It was the grammar of probability that dictated where the first sentences of cosmic structure would begin. Without this inherent quantum randomness, without this source of entropy, the post-inflation universe would have remained perfectly smooth, perfectly homogeneous. Gravity would have had nothing to grab onto, no seeds to amplify. The cosmos would be a silent, eternal, and featureless sea of particles, a story with a title but no text. The quantum fluctuations were the vital spark of randomness, the entropy-driven surprise that broke the symmetry and allowed the universe to begin its magnificent billion-year journey toward complexity and life. If the unfolding cosmic story has a villain, it would surely be the black hole, a region of space-time where gravity is so intense that nothing, not even light, can escape its clutches. For decades, they were seen as the ultimate endpoints of destruction, cosmic trash compactors that simply hoarded matter and erased information from the universe. But a revolution in our understanding, led by the brilliant insights of Jacob Bekenstein and Stephen Hawking, has completely rewritten this narrative. We now understand that black holes are not the antithesis of entropy. They are, in fact, its most profound and powerful expression. They are the universe's ultimate entropy engines. The story of this revelation begins with a seeming paradox. The second law of thermodynamics states that the total entropy of a closed system must always increase. But what happens if you throw a high-entropy object, like a box of hot gas, into a black hole? From the outside perspective, it simply vanishes. It seems like the entropy of the universe has mysteriously decreased, violating the most sacred law of physics. This was the puzzle that a young graduate student named Jacob Bekenstein tackled in the 1970s. His radical proposal was that black holes themselves must possess an enormous amount of entropy. He suggested that this entropy was not related to the volume of the black hole, as one might expect for a normal object, but to the surface area of its event horizon, the point of no return. The larger the black hole's horizon, the greater its entropy. At first, this idea was met with skepticism, most notably from Stephen Hawking, who initially argued against it. But in a stunning turnaround, Hawking's own subsequent work not only confirmed Bekenstein's idea, but also took it to a breathtaking new level. Hawking applied quantum mechanics to the space just outside a black hole's event horizon and discovered that these gravitational behemoths are not completely black after all. Due to quantum effects, they should slowly emit a faint glow of particles, now known as Hawking radiation. This radiation carries away energy, causing the black hole to very slowly lose mass and eventually evaporate over astronomical timescales. Hawking's calculations showed that the entropy of a black hole is precisely 1/4 of the area of its event horizon, measured in Planck units. This is a truly staggering number. A single stellar mass black hole can have an entropy billions of times greater than that of all the stars, planets, and gas in the observable universe combined. They are by far the most efficient repositories of disorder in existence. This discovery forged an unbreakable link between three seemingly separate domains: gravity, described by Einstein's general relativity; thermodynamics, the science of heat and entropy; and quantum mechanics, the physics of the very small. The event horizon, a gravitational boundary, was now also a measure of information content. This hinted at a much deeper reality, perhaps best described by the holographic principle, which suggests that all the information describing the three-dimensional interior of a region of space might actually be encoded on its two-dimensional boundary, like a cosmic hologram. A black hole's event horizon is the ultimate holographic plate, its surface area holding the entire story of everything that ever fell inside. So, black holes are not merely swallowing disorder, they are cosmic archivists meticulously recording it. When a star, a planet, or even a book falls into a black hole, its information isn't destroyed. According to this new view, it is scrambled and encoded onto the fabric of the event horizon itself. The black hole's entropy is a direct measure of the unimaginable number of ways that information can be arranged on that surface. But the story doesn't end with the black hole simply hoarding this information. Through the slow, patient trickle of Hawking radiation, that information is gradually, and in an incredibly scrambled form, released back into the universe. This process suggests that entropy is not a one-way street to a silent graveyard. It is a dynamic, cyclical process of storage, transformation, and release. Black holes are not just the final period in the sentence of a star's life. They are active participants in the universe's narrative, taking in complex information, processing it into its most fundamental form, and then slowly feeding it back into the cosmic ecosystem. They are the great recyclers of entropy, ensuring that the universe's story, though constantly changing form, is never truly lost. This astonishing connection between a black hole's surface area and its immense entropy points toward one of the most radical and beautiful ideas in modern physics, the holographic principle. It's a concept that sounds like it's straight out of science fiction, but it emerges directly from the mathematics of black holes and quantum gravity. The principle proposes a staggering limitation on reality, that all the information needed to perfectly describe everything within a three-dimensional volume of space, every particle, every force, every flutter of energy, can be entirely encoded on the two-dimensional boundary that surrounds it. It's the ultimate cosmic compression algorithm. Think of an ordinary hologram like the kind you might see on a credit card. A holographic image is a flat, two-dimensional surface. But when you shine a light through it, it projects a full, three-dimensional picture that you can look around. The key is that every tiny piece of the two-dimensional surface contains information about the entire three-dimensional object. The holographic principle suggests our universe might operate in a similar way. The three-dimensional world we experience, with its depth, its volume, its rich interior, might be a projection, a kind of illusion generated from information written on a distant, two-dimensional surface that surrounds us. And what is the language of that information? Entropy. The work of Bekenstein and Hawking showed us that for a black hole, the entropy, which is a measure of its hidden information, is precisely proportional to the area of its event horizon. The horizon is not a physical surface, it's a mathematical boundary, yet it behaves like a cosmic hard drive with its total storage capacity determined by its area. This implies that the ultimate fundamental bits of reality, the ones and zeros of the universe, might not be scattered throughout space. Instead, they might be painted, one per tiny Planck area, on the outermost surface of the cosmos. Let's try to grasp the scale of this idea. Imagine a perfect imaginary sphere drawn around the Earth. The holographic principle doesn't say that the information about Earth is stored on its surface. It says the information describing everything inside that sphere is encoded on the sphere's surface. Now expand that sphere to encompass our solar system, our galaxy, and eventually the entire observable universe. The principle suggests that a complete description of every event, every atom, every thought that has ever occurred within our cosmic horizon is somehow written on the spherical shell that defines the edge of what we can see. We and everything we know are a holographic projection from that distant surface. This transforms our understanding of entropy from a passive measure into an active, creative force. Entropy is no longer just a number telling us about disorder. It becomes the foundational syntax, the basic code of cosmic reality. The increase of entropy throughout the universe's history isn't just a slide toward equilibrium. It's the process of this cosmic hard drive writing more and more information onto the boundary as the interior volume expands and complexifies. The birth of a star, the formation of a planet, the evolution of life, these are not just events happening in space. They are events being meticulously transcribed onto the universe's outermost surface in the language of information entropy. If this is true, then the universe's first sentence, that initial low entropy state, was the first line of code written on this primordial screen. The subsequent unfolding of the cosmos is the continuous execution of that program, projecting the breathtakingly complex and dynamic three-dimensional world we inhabit. The holographic principle offers a profound unification, suggesting that gravity, quantum mechanics, and thermodynamics are all different facets of a single, deeper reality, a reality where information is the most fundamental currency, and entropy is the grammar that gives it structure and meaning. We are not just living in a universe described by physics. We may be living inside a cosmic hologram whose source code is written in the elegant, simple, and powerful language of entropy. But what if our universe, with its finely tuned beginning, isn't the only one? What if it's just a single volume in an infinite cosmic library? This is the staggering proposition of the Multiverse Hypothesis. In this grand view, our entire cosmos, from the Big Bang to its eventual fate, is merely one bubble in a frothing, eternal sea of universes, each with its own unique set of physical laws and initial conditions. Some of these sibling universes might have stronger gravity, making stars burn out in a flash. Others might have no nuclear forces at all, forever preventing atoms from ever forming. They represent every possible configuration of reality, a vast tapestry of what could be. Within this limitless ensemble, entropy takes on a new and profound role as the ultimate differentiator, the key variable that dictates which universes get to tell a story and which remain forever silent. Imagine walking through this library of realities. You would pull countless volumes from the shelves only to find them filled with nothing but blank pages. These are the universes that began with high entropy. They were born old, so to speak, already in a state of maximum disorder and thermal equilibrium. In these worlds, there is no gradient, no imbalance to drive change. Particles are spread perfectly evenly, temperatures are uniform everywhere, and the arrow of time is meaningless because nothing ever happens. They are static, eternal, and featureless cosmic deserts where the story never begins. Then, incredibly rarely, you would find a book like ours, a universe that started with an exceptionally low entropy, a state of exquisite and improbable order. This is the special dialect of disorder that allows for a narrative. This low entropy beginning is the wound-up spring, the potential energy that powers the entire cosmic drama. It allows gravity to clump matter into galaxies, it allows nuclear furnaces to ignite in stars, and it allows complex chemistry to arise on planets. It creates the conditions where life, and eventually conscious observers like us, can emerge to witness and ponder the tale. In the language of the multiverse, entropy becomes a selective filter. It is the criterion that separates the storytelling universes from the silent ones. Our existence isn't just a lucky accident within our universe. It is proof that we inhabit one of the exceedingly rare universes capable of generating any accidents at all. This perspective offers a powerful answer to the question of why our universe seems so finely tuned for complexity. It's not that the constants were magically set just for us. It's that we can only exist in a universe where they were set to allow for our kind of complexity. This is the anthropic principle applied on a multiversal scale. We find ourselves in a universe with low initial entropy for the same reason a fish finds itself in water. It's the only environment where it can exist. Our ability to ask the question about entropy's origin is itself a product of the very conditions we are trying to explain. In this vast library of possibilities, entropy is the author that wrote most volumes as empty prose, but in a precious few, it composed an epic. We are living inside one of those rare, beautiful, and story-rich exceptions. But to truly understand this, we have to ask a much deeper question. Where does time itself come from? The equations of fundamental physics, from Newton's laws to Einstein's relativity to quantum mechanics, are almost entirely time-symmetric. They work just as well if time runs forward or backward. There's nothing in the core laws of the universe that points an arrow and says, "This way." The shocking truth is that time, as we experience it, with a definite past, present, and future, is not a fundamental feature of the cosmos. It is an emergent property, and its emergence is almost entirely thanks to entropy. Think of a movie played in reverse. We instantly know it's wrong because it violates our understanding of cause and effect. We see shards of a broken vase leap up from the floor and reassemble themselves on the table. We see smoke pour back into a cigarette, becoming pristine tobacco. These events are not impossible according to the laws of physics. The individual molecular motions could, in theory, conspire to make it happen, but the probability is so infinitesimally small that we never witness it. This overwhelming statistical bias toward disorder is the engine that drives the arrow of time. Entropy increase provides the necessary asymmetry. It gives the universe a before and an after. The past is the state of lower entropy. The future is the state of higher entropy. This gradient is what makes history possible. Without it, every moment would be statistically identical to every other, and the concepts of memory, aging, and progress would be utterly meaningless. In this profound sense, entropy is far more than a passenger riding along in time. It is the clockmaker. It built the clock and set it ticking in one irrevocable direction. That initial, incredibly low entropy state after the Big Bang was the moment the clock was wound. It established a powerful gradient, a state of incredible potential that the universe has been rushing to equilibrate ever since. This relentless journey toward higher entropy is what we perceive as the flow of time. Every process we associate with time's passage, the cooling of stars, the weathering of mountains, the aging of our own bodies, is simply a local manifestation of this global journey toward equilibrium. Entropy writes each new moment into existence by making the previous moment statistically unreachable. The universe cannot backtrack because returning to a state of lower entropy is, for all practical purposes, impossible. It is forever moving forward, composing its history one irreversible event at a time. This makes entropy the ultimate chronologist of the cosmos. It doesn't just measure time, it generates the very conditions that make a temporal narrative possible. It ensures that the story has a coherent plot where causes always precede effects. It guarantees that the universe has a history worth telling, a sequence of events that builds upon itself, creating ever more complex and interesting structures along the way. The increasing disorder is the price paid for the universe's incredible creativity. It is the cost of having a story at all. So the next time you glance at a clock, remember you're not just seeing a measure of duration. You are witnessing the visible output of the universe's most fundamental creative process, the relentless, beautiful, and tragic unfolding of entropy, writing the story of everything, one irreversible tick at a time. Now, if we shift our gaze from the cosmic scale to our own planet, we encounter what seems like a glaring contradiction. Life appears to be a stunning rebellion against the universe's grand trend. A single cell divides and differentiates into the intricate, ordered structure of a living creature. A seed gathers scattered molecules from soil and air to build a towering, complex tree. Our own bodies are marvels of organization, maintaining a precise internal order against the relentless pull of chaos. It looks for all the world like life is reversing entropy, creating localized pockets of order in a universe sliding toward disorder. But this is a beautiful illusion. Life does not defy the second law of thermodynamics. It is one of its most elegant and sophisticated expressions. Organisms are not isolated systems. They are open systems, constantly exchanging energy and matter with their environment. And the secret to their incredible order is that they survive and thrive by exporting disorder outward. Think of your own body. You maintain a constant temperature of around 37 degrees Celsius, a highly ordered state compared to the varying temperatures outside. To do this, you burn fuel food. The process of metabolizing that food is incredibly inefficient. It generates waste heat, which you dissipate into your surroundings, and produces simpler, more disordered molecules like carbon dioxide and water. You are, in essence, a machine for taking in concentrated, high-quality energy, the complex chemical bonds in your food, and converting it into lower quality, dispersed energy, heat, and waste. You preserve your internal order by increasing the total entropy of the system that is you plus your environment. Your life is a continuous process of creating a small, local eddy of order in the stream of the universe, but you do it by pushing the current of disorder forward even faster elsewhere. Perhaps the most magnificent example of this is photosynthesis, the very foundation of most life on Earth. A plant sits in the sun, seemingly passive. But on a molecular level, it is performing an incredible feat of entropy accounting. It captures photons from the sun, which are a form of high-energy, low-entropy radiation. It uses that energy to take a simple, stable molecule, carbon dioxide, and a simple compound, water, and wrestle them into a fantastically complex and ordered molecule, glucose, a sugar. This builds the plant's structure and stores energy. From one perspective, this is a massive local decrease in entropy. The plant has created exquisite order from simpler parts. But the global picture tells the true story. The sun is a raging inferno of nuclear fusion, a massive source of high-entropy radiation. For every photon a plant uses to build order, the sun has poured out countless more that radiate out into the cold, empty void of space, their energy forever dispersed. The plant is effectively siphoning off a tiny, structured trickle from a vast, chaotic waterfall of solar entropy and using it to power its own growth. The overall entropy of the Earth-Sun system increases dramatically, and life is a breathtakingly beautiful byproduct of that process. This reframes evolution itself not as a march toward order, but as a spectacularly creative exploitation of entropy's flow. Evolution is a search algorithm driven by randomness, by genetic mutations, which are essentially errors in copying, little injections of disorder into the code of life. Most of these mutations are detrimental or neutral, but a few, by pure chance, create a new variation that allows an organism to more efficiently capture energy and export entropy. A slightly better enzyme for breaking down food, a more efficient lung for extracting oxygen, a sharper eye for spotting prey. These are all adaptations that allow an organism to better manage the energy flow through its system. They are better at turning the universal trend toward disorder into a personal strategy for survival and reproduction. In this way, entropy is the engine of natural selection. It provides the constant, relentless pressure that rewards any innovation that can more effectively harness energy gradients and dissipate them, turning potential into structure, movement, and ultimately, more life. So the universe isn't just using entropy to set the stage for life and then stepping back. It is using the relentless drive toward disorder to actively write the plot. The chaos of random mutation provides the raw material. The imperative to export entropy provides the selective pressure, and the result is the astonishing narrative of adaptation, diversification, and complexity that unfolds over billions of years. From the first self-replicating molecules in a primordial soup to the dazzling array of ecosystems we see today, life is the universe's most intricate and sustained method for increasing entropy. It is a story where chaos is not the enemy, but the essential fuel for creativity, turning the cosmic imperative of disorder into a brilliant, ongoing saga of survival and innovation. Now consider your own mind a swirling storm of thoughts, sensations, and memories. It might seem like a world apart from the cold equations of cosmology, but there is a profound and beautiful connection. Our consciousness, the very essence of our experience, operates on principles that are strikingly similar to information entropy. The brain is not a passive recorder of reality. It is an active, relentless processor of information, constantly engaged in the monumental task of filtering meaningful signals from a deafening roar of internal and external noise. Every sight, sound, and feeling is a torrent of data, and your brain's primary job is to reduce the overwhelming uncertainty of this input, to lower the local entropy of your perceptual world, so you can navigate it effectively. This mental filtering is what we experience as attention and focus. It's why you can listen to a single conversation in a crowded, noisy room, your brain suppressing the irrelevant chatter to highlight the salient signal. This process is the cornerstone of learning and perception. When you learn a new skill, like playing a musical instrument, the initial stages are clumsy and full of errors, a high entropy state of mental randomness. But with practice, your brain identifies and reinforces the successful neural pathways, reducing the mental entropy and making the skill automatic, orderly, and efficient. This is learning in its essence, the brain's way of creating internal order from chaos. But the magic of mental entropy isn't just about creating order, it's also the wellspring of creativity itself. A truly low entropy mind, one that is completely ordered and rigid, would be incapable of original thought. It would only produce predictable, repetitive outputs. Creativity requires a delicate balance, a certain amount of controlled chaos or mental entropy to generate novel combinations of ideas. Think of a poet searching for the right word or a scientist pondering a new hypothesis. Their minds are exploring a landscape of possibilities, allowing random associations to form until a new, elegant, and lower entropy solution emerges, the perfect metaphor or the elegant equation. This creative spark is a microcosm of the universe's own creative process, where quantum fluctuations, a form of physical randomness, seeded all cosmic structure. Your most innovative thoughts are born from your brain's ability to harness its own internal entropy, to use noise as a creative partner. This suggests a breathtaking possibility. If the universe's first sentence was indeed written in the dialect of entropy, then our human consciousness might be nature's way of learning to read that language. Our capacity for thought, for perceiving patterns in the stars or in the pages of a book, could be seen as a process of decoding the informational patterns that entropy has been writing into the cosmos for billions of years. This links the vast macrocosm to the intimate microcosm of our inner lives in a deeply meaningful way. It suggests we are not merely passive observers of a universe unfolding according to distant physical laws. We are active participants in entropy's grand, ongoing narrative. Our very act of perception, of learning, and of creating art and science is part of the universe's process of understanding itself. Each time we solve a problem, appreciate a beautiful piece of music, or feel a moment of awe looking at the night sky, we are engaging in a dialogue with the cosmos using the same fundamental currency, information shaped by entropy. Our minds are not separate from the physical universe. They are a particularly rich and complex manifestation of its most fundamental storytelling language. We are both the readers and the newest sentences in entropy's epic, a story that began with a single, simple state of order and has now evolved to the point where it can contemplate its own origins. This brings us to one of the most profound and personal questions we can ask. If the universe's story is being written by the relentless increase of entropy, dictating the arrow of time and the flow of information, where does that leave us? Do we have free will, or are our choices just an elaborate illusion, a predetermined part of entropy's grand narrative? This is not just an abstract puzzle for philosophers. It strikes at the very heart of our human experience, our sense of agency, and our place in the cosmos. On one side of this debate is a compellingly deterministic view. If every event is the direct result of prior physical causes, a chain reaction stretching all the way back to the initial conditions of the Big Bang, then our feeling of making a choice might be nothing more than a sophisticated neural computation playing out in our brains. In this view, the increase of entropy is simply the backdrop against which this predetermined script unfolds. Our lives, our decisions, even this very thought, all were encoded in that first low entropy state, and the universe is just executing the code. We are readers of a book that has already been written, merely turning the pages one by one, mistaking the progression of the plot for our own volition. Yet there is another, more liberating perspective, one that finds its roots in the very nature of entropy itself. Remember, entropy is fundamentally a measure of uncertainty and possibility. The future is a state of higher entropy than the past, meaning it holds a vastly greater number of possible arrangements. This inherent uncertainty, this branching tree of potential outcomes, might be the very thing that creates the opening for genuine choice. The universe does not dictate a single future. It presents a near-infinite array of probabilities. Our consciousness, our ability to reason and imagine, could be the mechanism that collapses these probabilities into a single reality. In this light, free will isn't the ability to defy physics, but the capacity to navigate and influence the probabilistic landscape that physics provides. The increasing entropy of the universe doesn't lock us into a single path. It provides the open field in which we can carve our own. This beautiful tension perfectly mirrors entropy's own dual character. It is both the author of a cosmic script and the provider of a blank page. The script is the unstoppable global trend toward disorder. The fact that the sun will eventually burn out and the universe will likely end in heat death. This is the overarching plot we cannot change, but the blank page is the local moment-to-moment uncertainty at the quantum level, in the weather, in the stock market, and in the electrochemical storms of our own brains. This is where the story gets its texture, its surprises, and its beauty. Our free will may exist in the creative space between these two scales. We are constrained by the larger narrative arc of the cosmos, yet we have immense freedom to write the sentences and paragraphs of our own lives within that grand framework. So, are we merely characters in entropy's story, or are we its co-authors? The answer may be both. The laws of physics provide the grammar and the syntax, the rules of the language. But we are the ones choosing the words, crafting the metaphors, and deciding what the story means. Every time we make a choice to be kind, to create art, to pursue knowledge, to love, we are not violating the laws of thermodynamics. We are fulfilling them in the most beautiful way possible. We are using the energy flow and information processing that entropy allows to inject meaning, purpose, and beauty into the cosmic narrative. Our free will is not a phantom. It is the universe's most sophisticated method for exploring its own potential, a way for entropy to not just increase, but to create, to feel, and to understand itself through us. This astonishing fine-tuning of our universe, from the force of gravity to the mass of an electron, extends to its very first and most crucial parameter, its initial low entropy. It's as if the cosmic dice were loaded from the very beginning, not for a generic outcome, but for one spectacularly specific result. The anthropic principle offers a powerful lens through which to view this apparent coincidence. In its simplest form, it states that the universe must be compatible with the conscious life that observes it. We shouldn't be surprised to find ourselves in a universe capable of producing us. It sounds almost tautological, but its implications are profound when applied to entropy. Consider the alternatives. If the universe had begun with a much higher level of entropy, it would have been born old, already in a state of maximum disorder and thermal equilibrium. In such a cosmos, particles would be spread perfectly evenly. There would be no temperature differences, no energy gradients, and no potential for work to be done. Gravity would have no lumps to amplify, stars would never ignite, and the cosmos would be a silent, static, and eternal fog, a story with a title but no text, utterly devoid of complexity or observers. Conversely, if the initial entropy were even lower than it was, the universe might have been so rigidly ordered, so locked into its initial perfect state, that change of any kind would be impossible. Fluctuations might never occur, quantum fields might never stir, and the arrow of time might not even exist. the cosmos would be a frozen, timeless sculpture, beautiful in its perfection but equally silent and sterile. For a universe to tell a story that includes characters, it needs a very specific starting point, one that is balanced precariously between absolute order and absolute chaos. This is the narrow window of possibility in which we find ourselves. Our universe's initial low entropy was not arbitrary. It was the golden ticket that allowed the entire narrative of complexity to unfold. It provided the necessary disequilibrium, the wound-up spring, that could slowly release its energy over billions of years, powering the formation of galaxies, the nuclear furnaces of stars, and the intricate chemical ballet of life. The anthropic principle suggests that entropy was not just a random initial condition. It was a prerequisite, a carefully set dial that had to be positioned within an exceedingly narrow range to allow for the eventual emergence of observers who could look back and wonder at it all. In this view, the universe isn't fine-tuned for life in general. It is fine-tuned for story. It is fine-tuned for a long, coherent, and increasingly complex narrative that has a beginning, a middle, and eventually an audience capable of understanding the plot. This transforms entropy from a blind, mechanical process into a deeply meaningful feature of reality. It becomes the universe's ingenious method for ensuring its own epic would have witnesses. By starting with that specific, low entropy state, the cosmos guaranteed that its journey toward higher entropy would be a journey of creation, not just dissolution. The increasing disorder is the very engine that drives the formation of structure, the evolution of species, and the dawn of consciousness. We are not accidental bystanders to this process. We are its most sophisticated product. Our ability to perceive the universe, to measure the cosmic microwave background, and to contemplate the nature of entropy itself, is the universe's way of becoming self-aware. The story needed an audience to give it meaning, and entropy wrote the conditions that made that audience inevitable. We are the universe comprehending its own first sentence. Read in the language it was originally written in. This human fascination with the interplay of chaos and order isn't a modern invention. It is a thread woven through the very fabric of our cultural history, echoing the universe's own foundational principles. Long before physicists had a word for it, ancient cultures were intuitively grasping the concept of creation, emerging from a primordial state of undifferentiated potential, a cosmic low entropy state. In Greek mythology, the very first thing to exist was chaos, a formless, yawning void from which the first gods and the ordered world eventually emerged. Similarly, in Hindu philosophy, the ultimate reality is Brahman, an infinite, unchanging, and undifferentiated consciousness from which the illusion of the manifold world, Maya, unfolds. The Norse spoke of Ginnungagap, a great abyss that existed before the world, and from whose interaction of fire and ice the first giant, Ymir, was born. These myths are more than just stories. They are humanity's first attempts to narrativize the cosmic process we now call entropy. They reflect a deep, intuitive understanding that existence requires a beginning of perfect, silent potential, a blank slate, from which the rich tapestry of reality can be painted through the introduction of distinction, structure, and inevitably disorder. We see this same dialogue between order and chaos play out in the evolution of human art, serving as a powerful metaphor for the universe's creative journey. For centuries, classical art often pursued ideals of perfect symmetry, balance, and realistic representation, a search for a kind of artistic low entropy. But the modern art movement, in particular, began to consciously embrace the aesthetic power of disorder. Take the work of an artist like Jackson Pollock. His iconic drip paintings might look like random chaos at first glance, but detailed analysis reveals they are generated through a controlled, complex process. The paint splatters exhibit fractal patterns, self-similar patterns that repeat at different scales, which are also found in coastlines, clouds, and galaxies. His art does not depict chaos, it is a controlled exploration of it. It captures a moment of dynamic, entropic process frozen in time, a beautiful snapshot of order and disorder in a delicate dance. This isn't destruction, it's a different kind of creation, one that mirrors the universe's method of building complexity from simple rules and random fluctuations. This artistic exploration extends beyond the canvas and into the very sounds we listen to. The genre of ambient and electronic music often incorporates elements of noise and generative randomness, creating soundscapes that feel both organic and structured. Composers use algorithms to create fractal music, where patterns repeat and vary in mathematically defined ways that mimic natural processes. Even in more traditional music, the tension between predictable melody and surprising harmony, between the structure of the rhythm and the improvisation of a jazz solo, reflects this universal theme. We find beauty not in pure order or pure chaos, but in the fertile ground where they meet. Our art, in its highest forms, becomes a conscious reflection of the cosmic process, a way for us to externalize and interact with the same fundamental forces that shaped the stars. We are not just observers of entropy, we are practitioners of it, using its principles to create meaning and evoke emotion. This profound resonance suggests something extraordinary, that the human impulse to create stories, art, and music might be more than just a cultural artifact. It could be a fundamental expression of the same physical laws that govern the cosmos. We are made of stardust, and our minds are shaped by a universe whose narrative is written in the language of entropy. It is only natural that our own creativity would mirror that same syntax. When a poet struggles to find the right word, they are sifting through a high-entropy field of possibilities to arrive at a perfect, low-entropy phrase that carries maximum meaning and minimal surprise. When a filmmaker builds suspense, they are carefully controlling the flow of information to the audience, managing the entropy of the plot to create shock, awe, or catharsis. Our storytelling itself, from the earliest campfire tales to the most complex novels, is a process of taking the chaotic raw material of human experience and imposing a narrative order upon it, creating a coherent arc with a beginning, middle, and end, much like the universe's own story from the Big Bang to heat death. In creating art, we are quite literally speaking the universe's native tongue, using the interplay of chaos and order to write our own small, beautiful verses in its grand, ongoing epic. Now let's bring this cosmic story down to earth, into the very devices you're using right now to watch this video. The digital age, it turns out, is a powerful new chapter in entropy's epic, written not in particles and energy, but in bits and bytes. The same concept of information entropy that Claude Shannon developed for telephone lines is now the fundamental engine of our technological world. It's the hidden force behind every compressed file you download, every secure message you send, and every artificial intelligence that learns from data. We are living through a revolution powered by the management of information disorder, and it's hurtling us toward a future that is both exhilarating and deeply uncertain. Think about data compression, the magic that lets you store thousands of photos on your phone or stream a high-definition movie. At its heart, compression is all about finding and eliminating redundancy, the predictable, low-entropy parts of a file. A completely random, high-entropy string of data is actually impossible to compress. There are no patterns to simplify, but a photo of a blue sky has a lot of predictable order. A compression algorithm like ZIP or JPEG works by ruthlessly identifying these orderly patterns. It finds the repeating elements and replaces them with a much shorter piece of code that says, in effect, repeat this blue pixel 1,000 times. It's a process of creating local order from potential chaos, of reducing the informational entropy of the file to make it smaller and more manageable. The compressed file is a state of lower entropy, but to achieve it, the algorithm must export disorder in the form of heat generated by the processor doing the work. It's a perfect digital mirror of a living cell maintaining its internal order by increasing entropy in its surroundings. This dance with entropy becomes even more critical in the realm of encryption, the art of keeping secrets. The entire foundation of modern cryptography, which protects everything from your bank transactions to private messages, relies on creating maximum entropy. A truly secure encryption key is one that is completely random and unpredictable. It has the highest possible information entropy. If a key has any pattern or order, any predictability, it becomes vulnerable to attack. Cryptographers strive to generate keys that are essentially digital Boltzmann brains, unique, random, and impossibly improbable to guess. The strength of your privacy is directly proportional to the entropy of your encryption key. Here, high entropy isn't a problem to be solved. It's the most valuable resource we have, the bedrock of trust and security in a connected world. But the most profound application of this principle is in the development of artificial intelligence. Machine learning algorithms, particularly the deep neural networks behind today's AI marvels, are essentially entropy reduction engines. They are presented with a massive, high-entropy dataset, a chaotic jumble of images, text, or sounds. The algorithm's task is to find patterns in this noise, to identify the underlying rules and relationships. During its training, it makes countless random guesses, a high-entropy process of trial and error. With each iteration, it compares its output to the desired result and adjusts its internal parameters, slowly sculpting away the wrong answers and reinforcing the correct pathways. This learning process is a direct analog to a physical system cooling down and settling into an ordered state. The trained AI model is a complex, low-entropy structure that has been carved out of a sea of data chaos. It has learned to export its initial uncertainty and arrive at a state that can make accurate predictions, recognize faces, or generate human-like text. In a very real sense, we are teaching machines to think by teaching them how to manage information entropy. This explosion of digital technology, however, has hurled us into a crisis that directly mirrors the universe's own fate. We are generating data at a truly astronomical rate, an ever-expanding ocean of emails, videos, sensor readings, and social media posts. This is our own version of the universe's heat death, a digital heat death, or an entropy crisis of information overload. The sheer volume of data is so vast that its potential meaning is drowning in its own noise. Finding a single, important piece of information in this digital universe is becoming as difficult as finding a specific atom in the entire cosmos. This isn't just a storage problem, it's a fundamental challenge of finding signal in the noise, of creating meaning from the chaos. How we choose to manage this deluge, what data we choose to keep, what we compress beyond recognition, and what we let fade into oblivion, will fundamentally shape the future narratives of our society, our history, and even our own identities. The universe used entropy to write its first sentence, and now we are using that same language to write our future, one that will be increasingly shaped by the AIs we are training to navigate the disorder we have created. This cosmic dance of entropy isn't just a grand spectacle happening out in the void. It's a process we are actively participating in here on Earth, and it brings us to a profound and urgent ethical crossroads. Every single action we take, from charging a phone to building a city, is part of a local exchange with the universal flow of entropy, and the choices we make are writing our chapter in the cosmic story. The second law isn't a suggestion, it's a fundamental framework of reality. We can't stop entropy from increasing, but we have a critical choice in how that increase manifests. Do we create a brief, brilliant flash of local order that results in a devastating wave of global disorder? Or do we learn to work with the grain of the universe, creating sustainable pockets of complexity that export their entropy in a way that is harmonious rather than destructive? This is the central ethical question posed by our understanding of entropy. Consider climate change, which is perhaps the most significant example of humanity mismanaging the entropic ledger. Fossil fuels, coal, oil, and gas are a form of incredibly low entropy, concentrated energy. They represent eons of ancient sunlight compressed by geological forces into a potent, highly ordered state. When we burn them in a century-long frenzy of industrialization, we are performing a massive, rapid entropy operation. We are taking that concentrated order and converting it into useful work, heat, and the disordered waste products of carbon dioxide and other pollutants. The problem isn't that we're increasing entropy, that's inevitable. The problem is the breathtaking speed and scale at which we are doing it, and the chaotic, harmful forms that the resulting disorder takes. We are creating a planetary-scale entropy dump in our atmosphere and oceans, disrupting the delicate, balanced systems that have allowed human civilization to flourish. Climate change is, in a very real sense, a story of entropy acceleration, a rapid, uncontrolled release of disordered energy that threatens the complex, ordered systems we depend on. This perspective reframes our entire relationship with sustainability. It's not about saving the planet in a sentimental sense. The planet and the universe will continue on their entropic journey with or without us. It's about wisely managing the flow of energy and disorder to preserve the conditions that allow our own complex, ordered society to persist. It's about understanding that every resource we use has an entropic cost. A mineral pulled from the earth, a forest cleared for farmland, a river dammed for electricity. These are all acts of creating local order for human purposes. The ethical imperative is to account for the global disorder this creates and to minimize its harmful impacts. This means moving from a linear economy of take, make, waste, which is a high entropy, destructive model, to a circular one focused on reuse, recycling, and regeneration, which more closely mirrors the efficient, cyclical processes we see in nature itself. This ethic of stewardship extends far beyond environmentalism into the realm of social equity. Entropy teaches us that systems naturally tend toward dispersion and equilibrium. Concentrated wealth and power are, like fossil fuels, states of incredibly low social entropy. History shows us that such concentrated order is inherently unstable and tends to disperse, often through violent or chaotic revolutions, a rapid and painful increase in social entropy. The ethical challenge, therefore, is to consciously build more equitable and just societies that avoid these dangerous concentrations in the first place. This means designing systems that distribute resources more fairly, that value diversity and resilience over rigid efficiency, and that create pathways for energy and opportunity to flow more freely. It is about learning to export social entropy not through conflict and collapse, but through peaceful, deliberate policies that promote fairness and opportunity, creating a more stable and harmonious form of widespread order. Recognizing entropy as a cosmic language, therefore, provides a powerful new moral compass. It urges us to align our human actions with the broader narrative of the universe, not in a passive way, but as conscious, responsible co-authors. Our task is to learn to read the entropic consequences of our choices, to see the invisible thermodynamic and informational costs behind our technologies, our economies, and our policies. It calls for a humility that acknowledges we are part of a much larger system with its own inexorable rules. Our chapter in cosmic history can be one of a species that briefly flickered into existence and consumed itself into oblivion through a reckless acceleration of disorder. Or it can be the story of a species that learned to harness energy with wisdom, that created beauty and knowledge, and that found a way to sustain its own delicate order for a graceful span of time, leaving a legacy of stewardship rather than chaos. The universe wrote the first sentence, but the next lines are ours to write. So what might that first cosmic sentence have actually sounded like, if we could somehow translate it from the language of physics into something we can comprehend? It wouldn't be a string of words, of course, but a set of impossibly precise numerical values, the fundamental constants of nature. Imagine these constants as the grammatical rules for reality. The strength of gravity, the mass of an electron, the precise value of the cosmological constant driving the universe's expansion, each is a specific setting that had to be dialed in with breathtaking accuracy for our particular story to unfold. If the gravitational constant were even slightly stronger, the universe would have collapsed back on itself immediately after the Big Bang, a story over in a flash. If it were slightly weaker, matter would never have clumped together to form the first stars. These constants are the universe's opening declaration, the foundational syntax that determined everything that would follow. They are the reason the universe didn't remain a featureless fog or immediately tear itself apart. They are the parameters that allowed entropy to increase in just the right way, at just the right pace, to build a cosmos of lasting structure and complexity. One compelling hypothesis for the literal first word is a quantum fluctuation. Even within the nothingness we might call a pre-cosmic vacuum, the rules of quantum mechanics tell us that something is always happening. Particles and energy flicker in and out of existence, borrowing from the vacuum for a fleeting moment. Most of these fluctuations vanish as quickly as they appear. But what if one didn't? What if a particularly significant fluctuation, a tiny speck of spacetime with an anomalously low entropy, failed to snap back? This wouldn't be a violent explosion from a single point, but more like a single, stable bubble of reality, nucleating out of the froth of nothingness. This bubble would possess that crucial, improbable state of low entropy, a tiny, ordered seed containing the potential for everything. And then, the mechanism of cosmic inflation would have seized upon this speck, acting as a runaway amplifier, stretching that quantum seed into an entire universe in an unimaginably small fraction of a second. In this view, the first sentence was a random but stable punctuation mark in the quantum vacuum that inflation then read aloud at a cosmic volume. Perhaps the most profound part of this first sentence is that it established the arrow of time itself. By starting in a state of such incredibly low entropy, the universe created a powerful gradient, a before and an after. This gradient is the reason time has a direction we perceive as forward. The universe was, in effect, wound up at the beginning, and everything that has happened since is the slow and intricate unwinding of that spring. The formation of galaxies, the birth and death of stars, the evolution of life on Earth, all of it is the universe evolving from a state of lower probability to a state of higher probability. That initial low entropy state is the ultimate past, the first moment from which all other moments flow. It is the reason we remember yesterday but not tomorrow. So the first sentence didn't just create space and matter, it created history. It wrote the very possibility of cause and effect into the fabric of existence. ensuring the cosmic story would have a narrative flow instead of being a random, senseless jumble of events. But can we move beyond this beautiful philosophical speculation and actually find physical evidence? Can we test the profound idea that entropy was the universe's first author? The answer is a resounding yes, and the proof is written across the entire sky, in the faint afterglow of creation itself. This evidence comes to us in the form of the cosmic microwave background radiation, or CMB. Imagine this as the oldest photograph ever taken, a snapshot of the universe when it was a mere 380,000 years old, a hot, dense plasma of particles and light. At that moment, the expanding cosmos cooled just enough for atoms to form, allowing light to decouple from matter and travel freely through space for the first time. That light has been traveling for over 13 billion years, and we can still detect it today as a faint microwave static that fills the entire universe, a cold echo of a fiery birth. This background radiation is astonishingly uniform, but it is not perfectly smooth. When we point our most sensitive telescopes, like the Planck satellite, at it, we detect tiny, minuscule variations in temperature fluctuations on the order of 1 part in 100,000. These tiny hot and cold spots are the anisotropies, the fossilized imprints of those primordial quantum fluctuations that were stretched to cosmic size during inflation. They are the gravitational seeds, the initial overdensities and underdensities that would eventually, over hundreds of millions of years, grow into the vast cosmic web of galaxies and voids we see today. This pattern is not random noise, it is a precise mathematical signature. It holds encoded within it a wealth of information about the infant universe, its composition, its density, its rate of expansion, and crucially, its initial conditions. By meticulously mapping these temperature variations, cosmologists are essentially reading the very first scribbles of structure, the handwriting of entropy from a time before time, as it began to inscribe its narrative onto the cosmos. The characteristics of this pattern are a direct window into the nature of those initial quantum jitters. The specific statistical distribution of the hot and cold spots, their sizes, and how they correlate with each other, matches the predictions of a universe that began in a very specific, low entropy state and was then shaped by a period of rapid inflationary expansion. It tells us that the initial fluctuations were indeed quantum in origin, random yet following a precise probabilistic distribution, exactly as the theory of entropy as a creative language would suggest. This cosmic fingerprint is so detailed that it allows scientists to measure the fundamental parameters of our universe with incredible precision, confirming that the initial conditions were exquisitely fine-tuned to allow for the eventual rise of complexity. The CMB is therefore our most powerful empirical link to the universe's first sentence. It is the preserved parchment showing the first words written in the dialect of entropy and probability. And the quest for evidence is accelerating into an even more thrilling new era with the dawn of gravitational wave astronomy. The first tremors of the Big Bang itself would have sent ripples through the very fabric of space-time primordial gravitational waves. These waves are a direct prediction of the inflationary period, and their detection would provide a completely independent and powerful line of evidence for the entire cosmic genesis story. Unlike light, gravitational waves travel almost unimpeded through the universe, meaning they could carry a pristine, undistorted signal from a time far earlier than the CMB, from the very first instance of inflation. Future observatories like the Space-Based Laser Interferometer Space Antenna, or LISA, will be hunting for these faint echoes from the beginning of everything. Finding this gravitational wave background would be like discovering the audio recording of the universe's first cry. It would give us a direct probe of the energy scales at which inflation occurred, telling us about the mechanism that took a quantum fluctuation and blew it up into a cosmos. It could reveal how the entropy of the gravitational field itself was set in those first moments, providing an even deeper understanding of how disorder was woven into the foundation of spacetime. This empirical pursuit transforms our grand philosophical wonderings into hard, testable science. We are no longer just speculating about the universe's first language. We are building sophisticated instruments to listen for its accent and grammar, seeking conclusive proof that the story of everything began not with a crystal-clear decree, but with a whisper of uncertainty, a quantum fluctuation that entropy then amplified into a billion-year epic of existence. And so we arrive at the final chapter of the cosmic story, an ending written not in fire or ice, but in a profound and chilling silence known as heat death. This is the ultimate destiny that the second law of thermodynamics has been guiding the universe toward since its very first moment. It is the state of maximum entropy, the point at which the universe has finally exhausted all its potential for change, all its gradients for work, and all its capacity for story. Imagine a vast, endless, and utterly dark ocean where the temperature is the same in every drop, a perfectly uniform lukewarm bath stretching across all of space. In this state, every star has long since burned out, every black hole has evaporated through Hawking radiation, and the fundamental particles themselves are so hopelessly dispersed that they may never interact again. The cosmos becomes a thin, featureless soup of photons and elementary particles, drifting eternally apart as the expansion of space continues to cool and dilute what little energy remains. There are no more whirlpools of matter to form galaxies, no more nuclear furnaces to ignite stars, and certainly no complex chemistry to spark life. The universe, in its final act, achieves a state of perfect equilibrium, a silence so complete that the very concept of time loses all meaning, as there are no longer any events to mark its passage. Yet, to view this as a tragic failure or a meaningless descent into oblivion is to misunderstand the narrative entirely. From the perspective of entropy as the universe's author, the heat death is not an error or a flaw. It is the final, perfect period at the end of a long and magnificent sentence. It represents the ultimate expression of all information and the full realization of all possibilities. Every potential arrangement of matter and energy that could have occurred within the constraints of the physical laws will have occurred. Every story that could be told will have been told. The universe will have fully unpacked the information compressed into its initial low entropy state, expressing every last bit of potential hidden within that first cosmic word. In this light, the heat death is the completion of the script, the final, quiet state of rest after the epic has concluded. It is the universe having said everything it possibly could say. This breathtaking finale forces upon us one of the most profound questions in all of cosmology. If entropy wrote the first sentence, is this cold, silent equilibrium truly the final, absolute end? Or could the story somehow continue? Some of the most brilliant minds in physics have refused to accept a single, finite narrative and have proposed breathtaking alternatives that allow the epic to continue. One of the most compelling is Sir Roger Penrose's conformal cyclic cosmology. This radical theory suggests that the universe's story is not a linear tale with one beginning and one end, but an endless series of cycles or eons. In this model, the far, far future heat death of our universe is not an end, but a transformation. As the universe expands toward infinity and all matter and energy dissipate into nothingness, the scale of the cosmos becomes so vast that the concept of distance itself loses all meaning. In this strange, empty state, the universe forgets its own scale. According to the intricate mathematics of conformal geometry, this maximally expanded, entropy-saturated state can be mathematically reinterpreted as a new singularity, a new Big Bang for a subsequent eon. Our universe's heat death becomes the low entropy birth of an entirely new cosmos, and the cycle begins again forever. In this view, entropy's final period is simultaneously its first word, and the story of existence is an infinite, self-renewing loop. Other theories venture into even more speculative territory, suggesting that our universe might be just one bubble in a vast and eternal multiverse, a concept we touched on earlier. In this sprawling cosmic landscape, new universes might be constantly bubbling into existence from a background quantum foam, each with its own unique laws and its own entropic destiny. While our particular universe may be destined for heat death, the greater multiverse would be teeming with endless births, lives, and deaths of countless other worlds. The overall narrative of reality would be an eternal tapestry, with individual threads beginning and ending, but the grand design continuing forever. This offers a different kind of immortality, not for our universe, but for the process of creation itself. The script that Enthropy is writing would be part of a much larger anthology, a library of universes where the story of existence never truly concludes. Whether the finale is a definitive end or a new beginning remains one of the greatest unsolved mysteries in science. But what is undeniable is the majestic arc that Enthropy has carved from that first moment to the last. It is the engine that drove the universe from a state of featureless simplicity to a temporary, glorious peak of complexity, giving rise to galaxies, stars, planets, life, and conscious beings capable of contemplating their own origins and fate. And it is the same force that will ultimately guide it back to a state of ultimate simplicity. This is not a tale of pointless decay, but a story of transformation and expression. The increasing entropy is the very reason anything interesting ever happened at all. It is the cost of having a history, the price paid for the privilege of existence and experience. The heat death, in all its silent, frozen grandeur, is the final, logical, and perhaps even beautiful fulfillment of that original creative impulse, the complete and utter expression of the first sentence written so long ago, when the universe began with a whisper of perfect order. For centuries, physics has been a tale of two separate kingdoms, each with its own ruler and its own set of laws. On the one hand, we have general relativity, which governs the majestic dance of planets, stars, and galaxies, the physics of the very large. It describes gravity not as a force, but as the elegant curvature of space-time itself, a geometric landscape where planets orbit simply by following the gentlest slopes. On the other hand, we have quantum mechanics, which rules the bizarre, probabilistic world of the very small, the realm of atoms and subatomic particles. Here, certainty is replaced by probability. Particles can be in two places at once, and empty space is a seething foam of virtual particles. Both theories are spectacularly successful in their own domains, but they are fundamentally, stubbornly incompatible. When their equations meet, such as at the center of a black hole or the moment of the Big Bang, the mathematics breaks down into nonsense, producing infinities that signal a complete failure of our understanding. This great schism is the single biggest problem in all of theoretical physics, and solving it, finding a theory of quantum gravity, is the holy grail of modern science. It is the quest to find a single, unified language that can describe all of reality, from the smallest quark to the largest cluster of galaxies. And remarkably, the key to unlocking this unified language might not be a new, exotic force, but a concept we've been exploring all along: entropy. The most compelling clue that entropy is the bridge between these two worlds comes from the most extreme objects in the universe, black holes. As we've seen, the work of Jacob Bekenstein and Stephen Hawking revealed that a black hole's entropy is proportional to the area of its event horizon. This was a shock. In every other system we know, entropy is proportional to volume. Think of the air in a room. The number of ways to arrange the molecules, and thus the entropy, depends on the three-dimensional space inside the room. But a black hole's entropy is a property of its two-dimensional surface. This bizarre fact led to the holographic principle, the radical idea that all the information needed to describe a three-dimensional volume of space might actually be encoded on its two-dimensional boundary. This is a direct violation of everything we intuitively believe about reality, and it points toward a profound truth that spacetime itself might not be fundamental. Instead, it could be an emergent property, a kind of illusion that arises from something deeper, and that something deeper appears to be information quantified by entropy. This is where the quest for quantum gravity takes a fascinating turn. The two leading candidates for a theory of everything, string theory and loop quantum gravity, both in their own ways find entropy at their core, hinting that it is the universal grammar they are both trying to decode. String theory proposes that the fundamental building blocks of reality are not point-like particles but incredibly tiny, vibrating strings. The different vibrations of these strings correspond to different particles like electrons or photons. In this framework, black holes are represented by a specific configuration of these strings, and when physicists calculate the number of ways these strings can vibrate to create a black hole of a given surface area, they find that the result exactly matches the Bekenstein-Hawking formula for entropy. The entropy is not just a property of the black hole, it is a direct count of the microscopic quantum states that make it up. This is a monumental achievement. It derives a law of gravity and thermodynamics from the quantum mechanics of strings. Loop quantum gravity takes a different but equally entropic path. It doesn't use strings but proposes that space itself is not smooth and continuous. Instead, it is woven from a fabric of tiny, discrete, loop-like threads of excited gravitational field. Think of spacetime not as a smooth sheet, but as a vast network of a billion tiny loops, like a cosmic chainmail. The area of any surface, including a black hole's event horizon, is quantized. It can only take on certain specific values, determined by the number of these tiny loops that pierce through it. When theorists count the number of ways these loops can intersect a surface to create a given area, they again find that the number of possible quantum states precisely reproduces the Bekenstein-Hawking entropy. Two completely different approaches, starting from wildly different assumptions, both arrive at the same destination. The entropy of a black hole is the fundamental key that links the quantum world to the gravitational world. This convergence is telling us something extraordinary. Entropy is not merely a phenomenon that happens within the universe. It appears to be a foundational principle that builds the universe. The quest for quantum gravity is pushing us toward a vision where space-time and gravity are not primary but emergent. They arise from the interactions of countless fundamental quantum bits, and the entropy of a system is the measure of the information stored in those bits. In this view, the smooth, curved spacetime of general relativity is a kind of average, large-scale picture, like the smooth surface of a lake that emerges from the chaotic motion of trillions of water molecules. The real action is happening at the microscopic quantum level, where entropy reigns supreme. This suggests that the universe's first sentence, the initial condition that set everything in motion, was not written in the language of geometry or particles, but in the language of information and probability, the language of entropy. It was a single, simple, low-entropy axiom that contained within it the potential for all the quantum complexity to come. Unifying gravity and quantum mechanics may ultimately be about learning to speak this language fluently, to see how the grammar of entropy generates the poetry of space-time, matter, and energy. It is a language that transcends our current physics, a Rosetta Stone for reality, waiting to be fully deciphered by the Einsteins of the future. Long before the first equations of thermodynamics were ever written, our ancestors were gazing at the stars and telling stories, trying to make sense of a seemingly chaotic world. And in these ancient myths, we find a profound and recurring theme: the idea that all of creation, all of order and structure, emerges from a primordial state of formless chaos. It's a narrative that echoes across continents and cultures, a deep, intuitive understanding of a cosmic process that science would later call entropy. In the vast, silent waters of Nun, the ancient Egyptians saw the origin of everything. This was not just water as we know it, but a concept of infinite, dark, undifferentiated potential, a cosmic nothingness that existed before time, before the gods, before distinction. From this chaotic abyss, the first god, Atum, willed himself into existence, a single point of order rising from the infinite disorder. He then created the first mound of land, the Benben stone, pushing back the waters and establishing the first stable ground. This was more than just a creation story. It was a metaphor for the very first act of cosmic organization, the initial separation of order from chaos, of something from nothing. It was an entropic genesis, where a state of maximum potential and minimum information, the formless Nun, gave rise to the first localized pocket of structure and meaning. A world away in the frozen north, the Norse poets sang of Ginnungagap, a great and yawning void that existed in the beginning. This was not an empty void, but a chaotic potential, a seething meeting place of primordial fire from Muspelheim and ice from Niflheim. Where the heat and the frost met in the center of Ginnungagap, a chemical reaction occurred, and from the dripping meltwater, the first being, the giant Ymir, was formed. Simultaneously, the primeval cow Audumbla licked the salty ice blocks, and with each lick, she revealed another part of the first god, Beri. Here, creation is not a singular act of will, but a process driven by the interaction of opposing, chaotic forces. The universe begins in a state of energetic imbalance, a thermodynamic gradient of hot and cold, and from that gradient, from that fundamental disorder, the first structures of life and divinity slowly coalesce. The Norse myth intuitively captures the idea that creation requires a departure from equilibrium, that something can only emerge from nothing if there is a tension, a difference, a potential for change, the very essence of what drives entropy's increase. This pattern is not unique to Egypt and Scandinavia. We see it in the Enuma Elish of Mesopotamia, where the young god Marduk battles the chaotic sea goddess Tiamat, slaying her and using her divided body to create the heavens and the earth, imposing order on her watery chaos. In Greek mythology, the very first thing to exist is chaos itself, a gaping void from which Gaia, earth, Tartarus, the underworld, and Eros, love, eventually emerge to begin the process of creation. In the Hindu Rigveda, the Nasadiya Sukta hymn contemplates the origin of the universe, describing a time when there was neither existence nor non-existence, only a dark, undifferentiated flux. These stories are far more than simple pre-scientific attempts to explain the world. They represent humanity's earliest philosophical struggle with the most fundamental questions of existence. Why is there something rather than nothing? And why does that something have form, structure, and law, instead of remaining an eternal, featureless fog? This cultural resonance is breathtaking. It suggests that for thousands of years, humanity has instinctively sensed that disorder is the default state of the cosmos, and that order is a precious, hard-won, and temporary achievement. These myths frame creation not as a one-time event that happened long ago, but as an ongoing battle against the ever-present pull of chaos. Every sunrise that pushes back the night, every spring that defeats winter, every society that builds laws against brutality, these are all modern echoes of Marduk fighting Tiamat, of autumn rising from none. They are local, ongoing acts of entropy reduction, small victories in the universe's grand trend toward dispersal. Our ancestors may not have had the mathematics of information theory, but they understood the narrative. They understood that the cosmos has a direction, that time has an arrow, and that the story of existence is the story of finding and creating meaning within a vast, indifferent background of potential chaos. In their own poetic language, they were describing the universe's first sentence, written in the dialect of probability and change, long before Boltzmann or Shannon gave it a formal name. These myths are the ancient, intuitive proof that the language of entropy is not just the language of physics, it is the fundamental language of story itself, written into the very fabric of how we understand our place in the cosmos. Look up at a spiral galaxy, and you'll witness one of the most breathtaking sights in the cosmos, a vast, swirling pinwheel of stars, dust, and gas. Yet for all its grandeur, it is not a perfect geometric form. Its arms are frayed, its structure is lopsided, and its core is a chaotic maelstrom of activity. This magnificent imperfection is not a design flaw. It is the signature of entropy at work. The galaxy's beautiful asymmetry is a direct result of gravitational interactions, random collisions, and the relentless pull of time, all processes driven by the universe's tendency toward disorder. This pattern repeats itself everywhere we look. Every snowflake forms around a microscopic dust grain, its intricate, six-branched pattern a unique product of the chaotic, turbulent conditions in the cloud where it was born. No two are ever alike because the precise path each one takes through the atmosphere is a story of countless random variables, a narrative written by entropy. Even the branching patterns of a tree or a river delta, which seem so elegantly designed, are actually the result of countless tiny, random events, a particle of soil deposited here, a drop of water eroding there. These systems find their stable, efficient forms not through top-down design, but through a bottom-up process of trial and error, of randomness finding order. This is the first crucial lesson entropy teaches us about beauty. Perfection is not only impossible, it is sterile. It is the slight deviations, the unique flaws, the scars of a history written by chance that give things their character, their identity, and their profound, captivating beauty. This celebration of imperfection finds one of its most powerful expressions in the Japanese aesthetic philosophy of wabi-sabi. Unlike Western classical ideals that often strive for symmetry, permanence, and flawless execution, wabi-sabi finds deep beauty in the very opposite. It cherishes the rustic and the simple, the imperfect and the incomplete. It sees profound value in the crack in a ceramic bowl, carefully repaired with gold lacquer in the art of kintsugi, because that crack tells the story of the bowl's use, its history, its life. The repair does not hide the damage, it highlights it, transforming a flaw into a unique feature, a testament to the object's journey. Wabi-sabi finds poetry in the moss-covered stone in a garden, the weathered and grayed grain of old wood, and the fleeting, melancholy beauty of cherry blossoms falling from the tree. This is an aesthetic deeply in tune with the principles of entropy. It recognizes that time, wear, and decay are not forces of destruction to be resisted, but essential processes that add depth, meaning, and a unique kind of value. An object that is mass-produced and perfect is identical to a million others, but an object that bears the marks of its age and use is utterly singular. Its history is physically inscribed upon it, a record of its interactions with the world. While Sabai doesn't just tolerate entropy, it reveres it, understanding that the most authentic and compelling beauty is not found in a state of pristine order, but in the graceful, evolving dance toward disorder. This philosophical shift allows us to see the entire universe as a work of art, with entropy as its primary artistic tool. If the universe were a painter, it would not use a ruler and a compass to create sterile, perfect circles and straight lines. It would be an abstract expressionist, flinging paint at the canvas with wild, chaotic energy, allowing the laws of physics to guide the pigments into the stunning, complex patterns we see in nebulae, weather systems, and neural networks. The artist knows that control is an illusion, and that the most interesting results come from embracing randomness and spontaneity. Entropy is the universe's way of introducing that crucial element of chance into its creative process. It is the reason every planet has unique topography, every zebra has a unique stripe pattern, and every human face is slightly asymmetrical. This relentless push toward disorder is what guarantees diversity and ensures that no two things are ever exactly the same. It is the engine of individuality. Without it, a universe that began in a state of perfect order would have remained a featureless, homogeneous soup, a cosmic museum with only one identical exhibit on display in every room. Entropy provides the variation, the mutation, the raw material upon which other forces like evolution and natural selection can act. It creates the possibility for innovation and surprise. In this grand view, every object, every moment, and every being becomes a unique verse in an epic, never-ending poem. The gnarled branch, the weathered face, the scattered leaves on a forest path, these are not mistakes in the composition. They are the composition. They are the direct and beautiful results of the universe's creative process, a process that values uniqueness and history over sterile perfection. The constant, gentle increase of entropy ensures that the poem is never finished, that the story is always being written. It means that value is not inherent in some impossible, permanent state of perfection, but is created through the very process of change and interaction. The universe is not a static sculpture to be admired from a distance. It is a dynamic, participatory performance, and the beautiful imperfections we see all around us are the evidence of its ongoing creative evolution. We are not just observers of this art. We are part of the medium itself, our own lives and experiences adding new, unique, and imperfect verses to the greatest masterpiece ever composed. Now consider the deep and often unspoken connection between our most powerful emotions and the silent, physical laws that govern the cosmos. It may seem like a vast leap from the thermodynamics of black holes to the feeling of joy in a tidy room or the anxiety of a cluttered desk, but this link is both profound and deeply personal. Our emotional lives are not separate from the universe's narrative of entropy. They are an intimate, internal reflection of it. We are biological systems, and like all systems, we are constantly navigating the flow between order and disorder. The calm satisfaction we feel when everything is in its right place, when our plans are neatly laid out and our environment is under control, is a psychological echo of a low entropy state. It's a feeling of equilibrium, of potential energy stored and ready for use, a moment of peace before the inevitable and necessary chaos of life begins again. Conversely, the unease that arises from chaos, a sudden crisis, a messy breakup, the overwhelming pile of unanswered emails, is a visceral reaction to a rapid, local increase in entropy. This isn't just a metaphor, it's a neurological reality. Our brains are prediction engines, constantly working to reduce the uncertainty of the world around us. When we are confronted with disorder, our cognitive load increases dramatically. We have to process more information, consider more possibilities, and expend more mental energy to find a path forward. This feeling of being overwhelmed is the subjective experience of a high entropy state in our personal lives. It's the mental equivalent of a cup of hot coffee cooling in a room, energy dispersing, possibilities multiplying, and our sense of control dissipating. This anxiety is not a character flaw. It is a deeply evolved response to an environment that has become less predictable and more demanding of our attention. Perhaps the most poignant emotional connection to entropy is found in the experience of nostalgia. This bittersweet longing for the past is more than just a fondness for old songs or faded photographs. It is often a yearning for a time we perceive as having lower entropy, a simpler, more orderly period in our personal history. We look back on childhood or a specific happy era and remember it as a time of clarity, when roles were defined, the future seemed certain, and the world felt more manageable. Of course, memory softens the edges and filters out the chaos that was undoubtedly present, but the feeling is real. Nostalgia is our mind's way of reaching back toward a personal low entropy state, a psychological anchor in the face of the present's constant and often disorienting change. It is an emotional manifestation of the second law's arrow, a longing for a past that feels statistically more improbable and therefore more precious with each passing day. This emotional landscape finds its most profound expression in the process of grief. The loss of a loved one is arguably the most devastating personal entropy event we can experience. It is a sudden, irreversible, and catastrophic increase in disorder within our world. The carefully structured reality we built with that person is shattered. Their future presence, which was a certainty in our mental model of the world, is gone, replaced by a void of unimaginable size and uncertainty. The initial stages of grief, denial, anger, bargaining are the psyche's frantic attempt to resist this new, unbearable entropy. It is the mind refusing to accept the new probability distribution of a world without that person, trying to find any possible way to reverse the irreversible. But grief, if allowed to follow its natural course, is ultimately a journey toward acceptance, and acceptance is not about forgetting or erasing the loss. It is the incredibly difficult work of psychological integration. It is the process of slowly, painfully reorganizing one's entire mental and emotional universe around this new reality. The shattered pieces are not discarded. They are gathered and reassembled into a new, different, and functional whole. The memory of the loved one is no longer a source of searing pain, but becomes a stable, ordered part of one's history, a source of strength and meaning. This is the emotional equivalent of achieving a new, stable equilibrium. The total entropy of the system, the bereaved person, and their expanded reality that now includes the loss has increased, but a new, rich, and complex order has been found within it. Grief, in its fullest expression, is the human spirit performing its own most heroic act of entropy management, transforming overwhelming chaos into a bearable and even meaningful new structure. In this way, our entire emotional experience can be seen as a continuous dialogue with the fundamental narrative of the universe. We are not just observing the increase of entropy from the outside, we are living it from within. Our joys, our fears, our longings, and our sorrows are the subjective texture of a cosmic process written into the fabric of physics itself. We are the universe feeling its own unfolding, comprehending the passage of time not through equations but through the heart. Our search for meaning in a world of constant change is the story of a conscious species learning to read the language of entropy not just in the stars, but in the quiet, everyday moments of its own existence. And yet, for all the cosmic drama of swirling galaxies and blazing stars, the overwhelming majority of the universe is not a stage for such spectacle, but a vast, silent, and nearly empty theater. Step outside the vibrant islands of matter, and you enter the true dominant reality of the cosmos, the cosmic voids. These are incomprehensibly large regions of space, millions of light years across, that contain almost nothing. No bright stars, no glowing nebulae, just a few scattered, lonely atoms per cubic meter, and an endless, crushing cold that hovers just a few degrees above absolute zero. If the universe's story is a book, then these voids are not the exciting chapters filled with action. They are the blank pages, the vast margins, the long, deep breaths between sentences. In these regions, entropy has reached a local maximum. The little matter that exists is so thinly dispersed, so perfectly and evenly spread out, that it has almost no potential left for interesting interactions. The energy is so dilute that it's effectively useless. It is a state of near-perfect equilibrium, a cosmic stillness so profound that time itself seems to slow to a crawl, with no events to mark its passage. This is the universe in its most relaxed, its most probable state. It is the background against which all the brilliant, low-entropy action of galaxies takes place. The voids are not a failure of the narrative, they are its necessary backdrop. They provide the dark canvas that makes the pinpricks of light so dazzlingly visible. Without these immense stretches of nothingness, the universe would be a blinding, homogeneous glare, a story with no paragraphs or pauses, just a single, overwhelming shout of light. But to call these voids truly empty is a mistake that would have made Einstein smile, for he showed us that empty space is not nothing. Even in the deepest, darkest void, the fabric of spacetime itself is alive with potential. This is due to the bizarre quantum phenomenon we call vacuum energy. According to quantum field theory, what we perceive as a complete vacuum is actually a seething, bubbling foam of virtual particles. Pairs of particles and antiparticles spontaneously flicker into and out of existence, borrowing energy from the vacuum for an infinitesimally short moment before annihilating each other and paying back the debt. This isn't just theoretical, it's a verified reality with measurable effects, like the Casimir effect, where two metal plates placed extremely close together in a vacuum are gently pushed together by the pressure of these quantum fluctuations outside them. This means that even the silent, blank pages of the cosmic void are not truly blank. They are filled with this faint, underlying hum of quantum potential, a static of existence written in the smallest possible font. This vacuum energy might even hold the key to one of the greatest mysteries in cosmology, dark energy. The observed acceleration of the universe's expansion is thought to be driven by some form of energy inherent to space itself, and this quantum jitter is a prime candidate. So the void is not passive. It is dynamically stretching the cosmos, actively writing the conditions for the next act on the largest scales, even as it appears utterly still and silent on smaller ones. Adding to this hidden depth is the ghostly presence of dark matter. We cannot see it as it does not emit, absorb, or reflect light, yet we know it is there from its overwhelming gravitational influence on galaxies. This mysterious substance is thought to form a vast, diffuse web that stretches throughout the entire cosmos, even and especially through these great voids. While normal, luminous matter has collapsed into the dense nodes of this web to form galaxies, the dark matter forms a much smoother, more extensive background field. It is the unseen scaffolding upon which the visible universe is built. So, within these apparent voids, this dark matter represents a hidden architecture, a massive amount of mass and information that is simply not in a form we can easily perceive. The page is not blank, it is written in invisible ink. This interplay between the vibrant nodes of galaxies and the silent stretches of void is essential for the pacing and rhythm of the cosmic story. A novel composed only of climactic action would be exhausting and ultimately meaningless. It is the quiet moments, the pauses for reflection, the chapters that develop character and setting, that give the action its weight and significance. In the same way, the cosmic voids provide the necessary negative space that defines the positive structures. They create the immense distances that allow galaxies to evolve in isolation, preventing them from constantly colliding and merging into a chaotic, homogeneous soup. They give the universe room to breathe, to expand, and to evolve over billions of years. The tension between the intense, localized action within galaxies and the profound stillness of the voids is what creates the narrative structure of the cosmos. It is a story that understands the power of silence, using the vast, empty spaces not as an absence of plot, but as a crucial literary device, building anticipation and giving weight to every brilliant, entropic event that punctuates the darkness. Yet for all its cosmic grandeur, this story of increasing disorder is often misunderstood as a one-way march toward dissolution and decay. We see the rust on a car, the fading of a photograph, the inevitable decline of our own bodies, and we label entropy as the villain of the universe, a relentless force of destruction. But this is a profound and limiting misconception. To see entropy only as an agent of chaos is to miss its most brilliant and beautiful role. It is the universe's primary creative force. The very same principle that scatters energy also builds the most exquisite structures imaginable. Consider a simple phase transition, like water freezing into ice. In its liquid state, water molecules zip and slide past one another in a relatively disordered, high-entropy dance. But as the temperature drops, something magical happens. The molecules begin to arrange themselves into a rigid, crystalline lattice, forming the intricate, six-branched symmetry of a snowflake. This appears to be a massive local decrease in entropy, a leap into perfect order. But the global picture tells the true story. The process of freezing releases latent heat into the surrounding environment. This dispersal of energy into the colder air represents a significant increase in the total entropy of the system. The beautiful, ordered crystal forms precisely because it is an efficient mechanism for the universe to export disorder. The snowflake is not a rebellion against the second law. It is a breathtaking byproduct of it, a delicate sculpture carved by the hand of entropy itself. This creative power extends far beyond simple physics and into the very engine of life. Evolution by natural selection is perhaps the most magnificent example of entropy's inventive potential. At its heart, evolution is driven by genetic mutations, random errors in the copying of DNA. These mutations are, in essence, little injections of informational entropy into the code of life. They are random, unpredictable, and often detrimental. But this randomness is the raw material for all innovation. A single, random change in a gene might lead to a slightly different protein, which might confer a slight advantage, a better ability to digest a new food source, a stronger resistance to a disease, or a more efficient way to capture sunlight. This advantage allows that organism to survive longer and reproduce more, passing that beneficial mutation on to the next generation. Over millions of years, this slow, patient process of random mutation followed by non-random selection builds staggering complexity from simplicity. The eye, the wing, the human brain, these are not the products of a top-down designer, but of bottom-up tinkering, where entropy provides the endless variations and natural selection chooses the most successful ones. Without that initial randomness, without that creative spark of disorder, evolution would have nothing to work with. Life would remain static and unchanging, a single, simple sentence repeated for eternity. Entropy, therefore, is not the enemy of life. It is its indispensable partner, the source of the variation that fuels adaptation, diversity, and the entire glorious saga of biology. This reframes our entire understanding of the cosmic narrative. Entropy is not a mindless vandal tearing down a finished masterpiece. It is the universe's most fundamental artist, and its primary medium is randomness. It begins with a blank canvas of perfect, featureless order, the low entropy singularity. Then, it introduces the first element of surprise, quantum fluctuations. With these initial random brushstrokes, the creative process begins. Gravity takes these slight imperfections and amplifies them, sculpting vast galactic sculptures. Nuclear fusion in stars uses the chaotic energy of collapsing gas clouds to forge new, heavier elements, the atomic pigments for future planets and life. On those planets, chemistry experiments with countless random combinations of molecules until, by chance, it stumbles upon one that can copy itself, launching the epic of evolution. At every single step, from the quantum to the cosmic, entropy is the engine of invention. It is the tool that allows the universe to explore its own possibilities, to try out new forms and structures, and to compose a story that is infinitely rich, surprising, and complex. The first sentence written in Entropy was not a declaration of decay. It was a promise of potential, a single, simple rule that contained within it the seeds of every galaxy, every star, every living creature, and every conscious mind that would ever come to be. The saga continues to unfold with every passing moment, as entropy tirelessly provides the raw material for the next chapter of cosmic creation. But what if our role is far more profound than just being readers of this cosmic story? Quantum mechanics, the rulebook for the subatomic world, presents us with a bizarre and thrilling possibility that the act of observation itself is not a passive process, but an active one that can fundamentally influence the reality being observed. This isn't about thoughts magically creating objects. It's about the fundamental nature of probability and how it resolves into a single, definite outcome. In the famous double-slit experiment, particles like electrons behave as waves of potential, creating an interference pattern on a screen behind two slits. They seem to go through both at once. But the moment you place a detector to see which slit an individual electron goes through, this wave-like behavior collapses. The electron acts like a single particle, and the interference pattern vanishes. Your simple act of measuring, of asking a specific question of the universe, forces a potentiality to choose a single, concrete reality. Now, let's translate this quantum weirdness into the language of entropy and information. Remember, entropy is a measure of uncertainty, of the number of possible states a system can be in. Before a measurement is taken, a quantum system exists in a superposition, a high entropy state of many possibilities all existing at once. The act of observation is a massive reduction in that local entropy. It takes a fog of potential and crystallizes it into a single, specific fact, a definite piece of information. In doing so, the observer exports entropy not necessarily as heat, but as a reduction of possibility. You have, in a very real sense, written a single, clear sentence into a page that was previously filled with every possible combination of words. You have created a point of order by resolving the uncertainty. This transforms our relationship with the universe from one of passive witness to active participant. Every time we measure something, every time we conduct an experiment, or even every time we simply pay attention to the world around us, we are engaging in this process of collapsing possibilities. We are not just discovering a pre-written story, we are forcing the universe to make choices, to specify details that were previously undecided. We are becoming co-authors in entropy's grand narrative. Our scientific instruments are like pens, and our curiosity is the ink. With every question we ask and every measurement we take, we are adding our own sentences, paragraphs, and chapters to the cosmic text. We are imposing our own localized order on the universe's inherent uncertainty, and in doing so, we are shaping the flow of how information and disorder unfold around us. This participatory role is both a tremendous responsibility and a source of incredible empowerment. It implies that our consciousness, our attention, and our choices are not insignificant epiphenomena in a deterministic machine. They are active forces in the ongoing creation of reality. What we choose to focus on, what we decide to measure, and how we interact with our environment all contribute to the specific way the universe's potential becomes actual. This doesn't grant us omnipotence. We are still bound by the larger grammar of physical laws and the overarching arrow of time set by that initial low entropy state. But it does give us immense creative agency within that framework. We are the universe's way of becoming self-aware, of looking back at itself, and through the act of observation, refining its own story. We are not merely characters in the book. We are the scribes holding the pen alongside the fundamental forces of nature, collaborating in the magnificent, never-ending writing of existence. Imagine a future where the most fundamental forces of nature, like gravity itself, are not primary ingredients of the universe, but rather side effects, emergent phenomena that arise from a much deeper, more fundamental principle. This is the radical promise of a concept known as entropic gravity, an idea that places entropy squarely at the center of our understanding of reality. Proposed by the Dutch theoretical physicist Erik Verland, entropic gravity suggests that what we perceive as the force of gravity is not a fundamental force at all, but an inevitable consequence of the universe's relentless drive toward higher entropy. Think of it like this: when a system tends toward disorder, it can manifest what looks like a force. A simple analogy is a crowded room. If you try to move through a dense crowd of people, you feel a kind of resistance, a pressure pushing back. This isn't because the people are actively repelling you with a fundamental force, but because your movement disrupts their own random, disordered motion, effectively increasing the local entropy. The force you feel is a statistical effect of the system trying to return to a state of higher probability. In entropic gravity, the fabric of spacetime itself behaves like that crowd. When a massive object like a planet sits in space, it creates a relative order in the quantum information that makes up spacetime around it. The natural tendency of the universe to maximize entropy then creates a kind of pressure that pushes other objects toward the massive one. We don't feel this as a pressure, of course. We interpret it as an attractive force, gravity. This is a breathtaking inversion of perspective. Instead of gravity causing things to fall, the act of something falling is simply the universe efficiently increasing its entropy. If this idea holds, it means that Newton's apple fell and Einstein's planets curved their orbits not because of a mysterious force, but because it was the statistically most probable thing to happen, the path of greatest disorder. Entropy wouldn't just be a feature of the universe, it would be the reason the universe has the shape and structure that it does. This revolutionary view is part of a much broader and more profound shift in physics, one that treats information as the most fundamental currency of reality. This field, known as quantum information theory, is rapidly changing how we think about the very stage upon which the cosmic drama plays out, space-time itself. The old view saw spacetime as a fixed, static background, a passive container within which particles moved and forces acted. The new view, heavily influenced by our understanding of black hole entropy and the holographic principle, suggests that spacetime is not fundamental. Instead, it might be an emergent property, a kind of illusion that arises from a vast, underlying network of quantum information. Imagine the pixels on your screen. Individually, they are just colored dots, but when you step back, those pixels arrange themselves to create the illusion of a continuous, smooth image. Quantum information theory proposes that spacetime works in a similar way. The smooth, continuous geometry we experience might be a large-scale approximation of a vast number of discrete, fundamental bits of information interacting with each other. In this model, what we call a particle or a wave is not a thing moving through space, but a specific pattern of correlations within this informational network. The force of gravity, the passage of time, even the three-dimensionality of our world, all of it could be a consequence of how this cosmic information is woven together and how its entropy evolves. This transforms the universe from a collection of things to a dynamic, evolving web of relationships, with entropy acting as the rulebook that governs how those relationships form and change. If these daring ideas are correct, they point toward a stunning unification of all physics. The quest for a theory of everything has long been stymied by the seemingly irreconcilable differences between the two pillars of modern physics: the quantum weirdness of the small and the geometric elegance of general relativity for the large. But if both gravity and spacetime itself emerge from a deeper informational reality described by entropy, then this century-old conflict simply melts away. The theory of everything might not be a single, overarching equation, but a set of principles about information processing and entropy generation. The different forces and particles we see would be like different words or grammatical structures in a single, universal language. This would mean that the universe's first sentence, the initial condition that launched everything, was not a geometric decree or a burst of energy, but an informational axiom, a single, simple rule about how information should be organized and how its entropy should be allowed to increase. The Big Bang would be the moment that rule was first applied, and the subsequent 13.8 billion years have been the unfolding consequence, the universe executing that initial program and expressing all the information that was latent within it. The future of science, therefore, may not be about finding smaller and smaller particles or more powerful telescopes, though those will surely play a role. It may be about learning to become fluent in this dialect of entropy and information. The physicists of tomorrow might look less like traditional scientists and more like cosmic linguists or programmers, deciphering the source code of reality. Their tools will be quantum computers, which themselves operate on the principles of quantum information and entanglement, allowing us to simulate and experiment with these fundamental informational processes in ways we can only dream of today. By creating and manipulating these complex informational systems, we might finally be able to read the universe's first sentence in its original language, understanding not just what the laws of nature are, but why they are the way they are. This journey is leading us to the precipice of a new understanding, one where entropy is no longer a footnote in a physics textbook, but the very syntax of existence, the fundamental language that wrote the first word and continues to compose the entire magnificent story. We have traveled an incredible path together, from that first silent speck of perfect order to the distant, cold silence of heat death, seeing how entropy is so much more than a measure of decay. It is the universe's original language, the foundational syntax that wrote the first sentence of existence and has been narrating every chapter since. This perspective does something remarkable. It threads together the hard equations of physics, the deep wonder of philosophy, and the profound beauty of poetry into a single, coherent tapestry. It shows us that what we often fear as disorder is, in fact, the very wellspring of all order, the engine of change, and the author of complexity. The cosmos did not begin with a shout of chaos, but with a whisper of incredible potential, a state of low entropy that set the stage for every galaxy, every star, every living thing, and every conscious thought that would ever arise. This grand view fundamentally reshapes our understanding of our own role within this epic. We are not merely passive spectators watching a predetermined story unfold on a cosmic screen. We are active, participatory beings within the narrative. Through the lens of quantum mechanics, we see that our very act of observation, our questioning and measurement, influences the way potentiality collapses into reality. We are not just reading the book of the universe, we are holding the pen, helping to write the sentences and paragraphs of our local experience. Our curiosity, our science, our art, and our choices are all part of the universe's process of understanding and expressing itself. We are the cosmos become self-aware, a way for the universe to look back upon itself and contemplate its own origins and its ultimate fate. This dual role as both reader and writer comes with a profound responsibility, a call to stewardship. Understanding entropy is not an abstract intellectual exercise. It has direct, urgent implications for how we live on this planet. The second law of thermodynamics is not a suggestion. It is a fundamental framework of reality. We cannot stop entropy from increasing, but we have a critical choice in how that increase manifests. We can choose to accelerate disorder in chaotic, harmful ways, burning through low entropy resources like fossil fuels and creating a planetary-scale entropy dump in our atmosphere. Or we can learn to work with the grain of the universe, creating sustainable, circular systems that manage the flow of energy and disorder with wisdom and foresight, ensuring that the conditions for our own complex, ordered civilization can persist. Our chapter in this cosmic story can be one of reckless consumption and collapse, or it can be one of graceful adaptation, wisdom, and beauty, a testament to a species that learned to understand its place and act with respect for the grand narrative it is a part of. So as we reach the end of this particular exploration, the invitation is to keep that sense of wonder alive. Let this be a beginning, not an end. The universe's story is still being written, and you have a part to play in it. Share your own thoughts and questions in the comments below. What does this perspective on entropy make you wonder about? Let's continue this conversation. If these deep dives into the mysteries of space and existence spark your curiosity, please subscribe to the channel for more journeys to the edges of our understanding. Give this video a like if it made you see disorder in a new light, and share it with someone who loves to ponder the big questions. Never stop questioning, never stop exploring, and never forget that you are an integral part of the universe's greatest, most ongoing story. But the conversation doesn't have to end here. If this journey into the heart of entropy has lit a spark of curiosity, there are incredible books that dive even deeper into these mind-bending ideas. Carlo Rovelli's The Order of Time is a beautiful, almost poetic exploration of how our perception of time is intertwined with entropy, while Sean Carroll's From Eternity to Here offers a masterful and comprehensive look at the arrow of time and the universe's initial conditions. I've put links to both of these books along with some other fascinating resources in the video description below for you to check out. The real magic, though, happens when we share our perspectives. I'd love to hear how this view of entropy is shaping your own understanding of reality. Does it change how you see the everyday world, from a melting ice cube to the passage of your own life? Leave a comment below and let's keep this discussion going. If this video opened a new door of wonder for you, giving it a like really helps others discover this content and join our community of cosmic enthusiasts. Sharing it with someone you know who loves a good mystery about the universe is one of the best ways to spread the curiosity. And if you haven't already, hit that subscribe button and tap the bell so you don't miss our next adventure as we continue to explore the deepest mysteries of space, time, and existence. Thank you for watching, and never